Let's talk about two types of solids. Very simple. Solids are, we saw that the solids are something like this, in which the particles are very tightly close to each other, right? Now we have two types of solids, the crystalline solids and amorphous solids. So let's first talk about the crystalline solids. What are the crystalline solids? They have a very regular arrangement. Now, they are closely packed in both, but they have a regular arrangement. That means they are very predictable. So as we see here, the first row in here have a blue, white, regular arrangement. The second has a yellow, black, and then it goes on like that. It is very predictable. It's very regular. So you can predict what goes on in here. It will be a blue atom. So we know that it has a regular arrangement and it's a long range order. You can predict the next particle or the type of the next particle up to a very long distance, right? Now, this might have some defects, but we'll talk about these things later. But for understanding as of now, we have to understand that crystalline solids have a regular arrangement, very predictable, and they are very predictable for a long distance, right? The case is different for an amorphous solid. The amorphous solids are solids, nevertheless, they are very closely packed, but there is no order. Everything is in chaos. It's like it's chaotic. It's haphazard. So there's no predictability about what's the next type of atom this can house in here. So it's an irregular arrangement of atoms and a short range order. But what I mean by short range order is there might be some kind of repeatability here. That, okay, you have a white and then a gap and then a white. There can be small, but there is no guarantee that after this you'll again get a white. There is no guarantee here. This can become blue. So even though there is a small bit of predictability on a small range, it has a short range order. This cannot continue for long distances as compared to the crystalline solids. We'll understand more about crystalline solids and how they behave and what examples in some later videos, but for now we should understand what's the difference between a crystalline and an amorphous solid is. Okay, so there are two very important properties, types of properties called the isotropic properties and the anisotropic properties. So what's the difference? Anisotropic properties depend on the direction of visualization. For example, if light travels from the first row, we see that the light that travels will behave differently if it travels from this direction, because the light encounters blue, white. But the moment the light travels in this direction, it encounters a yellow, black. While when it travels from this direction, this has a different arrangement. So depending upon which direction light is traveling, it will behave differently. So that is why this is an anisotropic behavior, right? So crystalline solids are behaving like anisotropics because they depend on the direction. Now, isotropic are those properties that do not depend on the direction. Why? Because they are the same from all the directions. For example, if light travels from this direction, this light sees chaos in this direction because there is no order. If it travels in this direction, there's still no order. Because this direction, still no order. So if it is a chaos, it's chaos. Chaos has no types. So like a Rubik's Cube, if it is not, if it is not solved, it's not solved. I mean, it's unsolved. It's like a chaos. So from every direction, the property remains the same, right? So for that, we call it isotropic. So amorphous solids are isotropic. Crystallines are not, because it will behave differently from different directions. Amorphous solids are isotropic because of the same reason. So liquids and gas also, because they are so haphazard and there is no order. So if amorphous solids behave as isotropic, liquids and gas are bound to behave as isotropic, right? So this is a very simple concept, might be counterintuitive, but if you stop and think about it, it will make sense to you. I have taken an example of Kit Kat. So for example, if you have a Kit Kat, so if you have a layer of wafer and a layer of chocolate and a layer of wafer, right? So if you go from this, it's a different property. So if light travels, you're seeing different things. If you travel from this direction, you're seeing different things. So the properties are changing in the direction in which you are attempting to see, and that is why it's an isotropic behavior, right? It's an isotropic. So isotropic, on the other hand, I have given an example of an Indian brand of snacks in which you have a whole mixture of things with different kinds of nuts and different kinds of snacks, and it's all mixed up into a very delicious mixture. You can try that if you want. And if you take a scoop and taste it, it just tastes the same on every scoop, although there's no particular arrangement in that. So if you take a scoop and visualize it, it still looks the same in every other scoop. So that is why it is isotropic. It's the same thing goes for amorphous. Because it's an irregular arrangement, the properties are isotropic, because chaos has no one, like chaos is a chaos. It has no different types of chaos in there. So I hope this makes sense. Let's move on to the next phase, which deals with temperature and phase change.